Hello. In this presentation, we're going to look at an introduction into time domain reflectometry and how these concepts relate to the settings when using a network analyzer for the measurement. So what actually is time domain reflectometry, or what's commonly known as TDR? Well, it's a measurement technique that allows us to launch a stimulus signal into an homogeneous medium, i.e. a cable or PCB board, whilst at the same time observing the response in time of any reflection signal that comes back due to any discontinuities that may occur across the structure. Applications of TDR include cable fault location, or more commonly known as distance to fault, direct impedance or mismatch measurements, for example on strip line microstrip structures or even test fixtures. TDR allows us to simplify filter tuning by characterizing the resonators and coupling apertures within the filter structure. And we can also use time domain gating to remove any unwanted effects due to discontinuities within our structure. And finally, a measurement which is not strictly TDR as it's based on a time domain transmission measurement, but we're seeing more signal integrity based applications now that allow us to measure parameters like rise time, balance line measurements like intra and inter-pair skews, near-end and far-end crosstalk, and more advanced measurements like eye diagram analysis to characterize the bandwidth of our structures. So let's look at a graphical representation of the time domain measurement. Now, although our network analyzer is a frequency domain instrument, to better understand what's going on, we're going to relate the measurement in the time domain first. So let's start by looking on the left-hand side where we have a piece of test equipment that allows us to generate a pulse that we're going to use to send into our structure here. And in this case here, our structure or DUT is a printed circuit board where we have a 50 ohm line, and along the length of the line we have a number of wires that will cause the signal to be distorted and reflected back to the source where it can be measured by the receivers. We can use the same analogy as in radar theory, where we're using the signal to bounce off a target and get reflected back to the receiver. So here's our pulse coming out, hits the first reflection and the second reflection, and then the receiver then measures those, processes the data. Then on the display, we see a signal of amplitude versus time of the reflections along the path of the DUT that we're measuring. So we can see that as we send the pulse into an unknown structure, we can then observe the discontinuities versus time. At each point, a percentage of the energy is reflected back to the source, so the magnitude of each reflection gives us an indication of the actual observed mismatch at this point. Now let's look at the situation where the device under test, the wire holes are spaced much more closely together. So as the pulse comes from the source, we hit the first discontinuity and then the second straight afterwards. So they actually sit side by side. As the data is processed on the display, we see that pulse 1 and pulse 2 are actually indistinguishable. So we can no longer resolve the two different wire holes. So when we're analyzing closely spaced discontinuities, the observable resolution is related to the pulse width used for the stimulus. Closely spaced reflections are no longer resolvable and appear simply as one. To enable us to overcome this limitation, we must look to reduce the pulse width that we're using to stimulate the DUT with, and hence give us a finer resolution. Here we can see the narrower pulse hits the first discontinuity and then the second one just afterwards, but now we have a separation between them. As this is processed by the analyzer, then we can see on the display clearly resolving pulse 1 and pulse 2 separated in time. So reducing the pulse width delivers us a finer resolution to resolve closely spaced discontinuities. So we've seen how pulses in the time domain can be used to stimulate a device and look at the discontinuities versus time, or ultimately distance. But fundamentally, how are we going to make this measurement with a network analyzer, which is a frequency domain instrument? So mathematically, we know that we can relate the time domain to the frequency domain via the Fourier transformation. and inversely from the frequency domain to the time domain with the inverse Fourier transformation. Now at this stage I don't want to go into mathematics here, we don't have to understand Laplace transforms here to know what's going on, but what I want to do is really just illustrate how we can make a pulse in the time domain from the frequency spectra in the frequency domain. So let's start firstly with the sine wave. This is made up of an individual fundamental frequency. If we then add the odd harmonic, so starting with the third harmonic, we can see then in the time domain how the two sine waves add together, and we continue it and add the fifth harmonic here, so the next odd harmonic, and they see how they add together here, and the resulting waveform starts to look very similar to a square wave. But let's continue with the odd harmonics and let's add the seventh harmonic and finally the ninth harmonic. And now you can see that we end up with something that's very, very resemblant of a rectangular square pulse. And so we can create a square pulse in the time domain simply by summing up all of the odd harmonic frequency components within the frequency domain. So to understand this further, let's look at the pulse and its effect on the spectrum in the frequency domain. So firstly, we know that a pulse spectrum in the time domain ends up looking like this familiar sine x over x response. So the envelope of the spectra give us this characteristic curve. The pulse width in the time domain effectively is giving us the position of this first dip in the pulse spectra here in the frequency domain, and they're inversely related. So the bandwidth of the pulse is inversely related to the width of the pulse in the time domain. So consequently, as we narrow our pulse, because we want to have better time resolution, we end up spreading the frequency spectrum over a wider bandwidth. And so from this we can conclude that to achieve better resolution in the time domain, then we must use a wider measurement in the frequency domain to perform our TDR measurement. Now, another characteristic of our pulse measurement in the time domain is the pulse repetition rate, or how frequently the pulse is regenerated and sent into the structure that we're measuring. So let's see an example here, again with our PCB board. Here comes our first pulse. Hits the first fire, we get a discontinuity reflected back, and then we get a second discontinuity, but the pulse repeats. So actually, we see a second pulse from the first via hole being reflected back into the receiver before the second via actually has time to travel back. So when this gets processed on the analyzer, what we now see is something that doesn't really represent the real picture of what's going on. We actually see some aliasing here. So we see two pulses from the first via and then the second pulse from the second via. So the pulse repetition rate defines how far into the structure that we can analyze before we start to see this repeated sequence again, which is known as the unambiguous range or the alias-free measurement range. So what effect does the pulse repetition rate have on the frequency spectrum? So we know that as we look at this repeating pulse, then in the frequency spectrum we're going to see this classic sine x over x envelope. The pulse period or the pulse repetition rate defines how closely spaced these frequency spectra are. So the pulse repetition frequency is 1 over the pulse period. They're inversely related. What happens when we increase the pulse period? Then the frequency spectra get closer together. So as the pulse period is increased, the spacing between the spectral lines is decreased. So we can conclude from this that reducing the frequency spacing between the line spectrum, or ultimately the step size number of points that we would have on the network analyzer, increases the pulse repetition rate, and hence the maximum distance that we can see into the structure of the device that we're measuring before we see any aliasing. So the last thing we want to consider here is something known as windowing functions, and this is a consequence of the Fourier transformation that we will use to convolve the frequency domain information measured by the network analyzer into the wanted time domain. So to start with, we have our frequency measurement that we're making. So here we can see there's the frequency response of the structure that we're measuring. And the FFT function will give us a negative image of that. So it's not strictly negative frequency, it's simply the phasor rotating in the opposite direction, but it's how we resolve the sines and cosines in the transformation. And ideally, to get a narrow pulse, then we want to sample an infinitely large bandwidth in the frequency domain, but our real network analyzer has a limited bandwidth. So we end up with a frequency response which is truncated by a rectangular filter because of the limitations of our measurement. And to make this accurate, we should also mirror this here on the left-hand side as well. Now, because of this truncation effect here, we can think about the frequency domain information being multiplied by this sin x over x response we saw with the pulse measurement. So in the time domain, this truncated frequency response ends up giving us some unwanted ripples in the time domain. So we can see this ringing effect moving out from the wanted response. Now, we can remove these ripples, or at least try and mitigate them by using a windowing function. And there's many different types of windowing filters available on network analyzers, but we're just going to use the standard one here, which is the Hanning window. And we can see that this has reduced those ripples, but at the consequence of widening up the frequency response. So the effect of applying the window has made our measurement better in terms of these ripples either side of the response, but it's widened up the response so that now our resolution has been compromised a little bit. So let's finish up by concluding what we have learned. Time domain reflectometry, or TDR, is a very powerful tool to analyze the makeup of various structures versus time or distance. To resolve smaller discontinuities, a finer pulse width is required, resulting in a wider span in the frequency domain and thus putting greater demands on the upper frequency range of the network analyzer being used. The unambiguous range, or alias-free range, is the longest distance you can measure into a structure before the measurement is repeated again. This is proportional to the frequency step size or number of points. The truncated frequency spectrum due to the finite span of the network analyzer causes ripples to occur in the time domain. These can be mitigated by using windowing functions at the cost of decreasing the time resolution of the overall measurement. Thank you for watching this video on time domain reflectometry basics.